Hey guys, and welcome to the seventh, I think, video of radioactivity and particles. And this is actually in response to a request that we do a video about hydrogen bombs and how they work and everything. So yeah, I'll try to make this relatively easy to understand, using some simple basic principles which we've learned already in the radioactivity chapter. So first of all, I'd like to say that I'm addressing the Teller-Ulam design by Edward Teller and Stanislaw Ulam. And I would just like to state right now that this kind of bomb is much stronger than your conventional fission bomb. Um, Hundreds, thousands of times stronger than the bombs exploded in Hiroshima and Nagasaki. Those look like babies compared to these bombs. So what makes them so powerful? Well, it's the really interesting and special design, which combines both the ideas of fusion and fission. So not just fission this time, both fusion and fission, because we know that they both produce a hell of a lot of energy. So first, let's talk about the requirements for fusion, which is going to clarify some things later when I talk about the design of the bomb. Well, the requirements for fusion are basically extremely high temperatures, or sorry, extremely high pressures. And this is usually related to extremely high temperatures, although pressures can be caused by making the volume extremely small as well. And of course, sufficiently light elements, such as hydrogen. Of course, hydrogen is the prime example. Fusion can occur with heavier elements, but usually we just use hydrogen because it's the easiest. Um, Okay, let's get started by talking about the design of the bomb. Well, in a bomb such as this, we have two parts, the primary part and the secondary part. The primary part is going to be focused on fission, the secondary part is going to be focused on fusion. And this fission fuel is made of uranium most of the time. And as we see in the secondary part, it's a bit more complex. We've got this kind of tube, and we've got a plutonium rod in the middle, which undergoes fission. The outer casings are made of uranium, which is also going to undergo fission. And this green stuff that we see here is the fusion fuel, which is lithium deuteride. Um, I'll explain. Well, technically, if you want a hydrogen fusion, you've got to have some hydrogen, and that's the deuteride. However, just hydrogen is a really hard to control gas. So what they do is they bond it with lithium to create lithium deuteride, which is a solid and much easier to handle. But as you can see, this doesn't exactly hinder the process one bit, as they exploit this even though it has some lithium in it, which is not hydrogen. So theoretically, it should be harder to fuse, but they exploit this later on. And yeah, let's get started on talking about the stages of the explosion. Okay, stage one. So in the primary, we've got all this uranium, and it undergoes fission by some explosives in the primary part, which simply enough just cause the uranium to undergo fission. Stage two. What happens now is that due to the fission, it emits tons of X-rays, and these X-rays heat up the uranium casing in massive amounts that they shoot outwards and expand. And this exerts a massive pressure on the secondary bit. So much pressure in the shock waves that it actually induces fission in the plutonium rod. So all this pressure is just pushing in and causing the plutonium to undergo fission. And this pressure is also squeezing the fusion fuel, making it more likely to undergo fusion. And so yeah, this plutonium in the middle starts to fizz, if that's the right term. And what this does is it creates incredible amounts of heat in the fusion fuel. And also, we recall that during a fission reaction, neutrons are produced. These neutrons collide with the lithium and the lithium deuteride and produce helium and hydrogen. So in this way, it's also using the lithium to create hydrogen, which is kind of taking away the problem, even though you've still got helium, which is kind of a byproduct of this. But yeah, it just generally splits up the lithium into deuterium and tritium, which are two isotopes of hydrogen which are easily fusible. So that's stage 3. And in stage 4, well, let's say that we take this classic fusion reaction, deuterium plus deuterium fuse together to create helium. And in this fusion reaction, another byproduct is also a neutron. And if we recall, if neutrons smash into uranium, then they cause the uranium to undergo fission. So when this happens, the outer casing, which is made of uranium, all completely undergoes fission. And this creates more radiation and more heat. So if we look at the total energy produced by this bomb, we see that it's the energy created from the nuclear fuel fission, from the primary segment, and also the energy created from the plutonium fission, the plutonium rod in the middle. And aside from that, we also have the energy from hydrogen fusion and energy from the fission of the uranium casing caused by the hydrogen fusion. And basically, that's a lot of energy, and this causes a massive, massive explosion. The biggest explosion, I think, is 50. It produces as much energy as 50 megatons of TNT, 50 million tons of TNT, and this was the Tsar Bomba, or King of Bombs, made in Soviet Russia, which is actually the most powerful weapon ever detonated by the human race. So yeah, that's quite interesting, the inner workings of hydrogen bombs. Thanks to whoever sent this request. And yeah, thanks for watching, basically. Please comment, rate, subscribe. And of course, commenting is extremely useful. Through that, you can ask questions that we perhaps have not answered. You can maybe say that I'm going a bit too fast or a bit too slow. We just basically want to improve, and we need your help doing that with some feedback. So, yeah, thanks for watching. Make sure to check out some of the other videos we have on physics topics and a bit of chemistry as well. And yeah, have a good day. I'll see you next time. And goodbye.